All right, I think we're about ready to get started. So thank you all for coming out to this tutorial. Welcome to PyCon. If it's anyone's first PyCon, especially welcome to PyCon. I'm glad you're here. It's one of my favorite times of the year. I've got a couple quick announcements before we get started with the tutorial proper. There's a survey link for this tutorial that I could read for you, but that's not useful to anyone, so I'm just going to post it at the end so that people can go to it after the fact. There's going to be an AM break at 10:15 in the lobby. It says the snacks go quickly, so please let your group out at the right time, which is a note for me, not for you. And then lunch is going to be at 12:20, or from 12:20 to 1:20 in Hall A. And at lunch, there's going to be a section for if you have dietary needs. There's going to be a sort of clearly marked section for you. All right. I think we're about good to go. Can everyone hear me okay? Cool. I'm going to try to do my best to sort of get the text up to sizes that are going to be legible in the back. So if I show you a slide and you can't read it at all, just raise your hand and I'll try to zoom it in to the best of my ability. So welcome. This is Foundations of Numerical Computing. If anyone hasn't already gotten set up with the exercises, you can go to pycon-exercises.partiallyapplied.com. We're running a Jupyter server there where you can get all the notebooks and you can use those without having to set up a scientific Python environment. When you get there, your username is going to be whatever you want. Password is going to be PyCon 2018. I'm going to leave this now, but when we switch to the next exercises, you'll be able to move to that. Cool, so a little bit about me. My name is Scott Sanderson. I'm a senior engineer at Quantopian. Quantopian is a company that builds tools for strangers on the internet to write quantitative trading strategies in Python. So my day job is essentially to write environments and tools to allow people to do quantitative finance in Python. And pretty much all of those tools are built on top of the foundation of NumPy and Pandas and SciPy and the other numerical Python ecosystem tools. So what's the goal of this tutorial? So the goal of this tutorial, in my mind, is to help you effectively solve numerically intensive problems in Python. In practice, what that usually means is that you're going to be using NumPy, at least as sort of the foundations of your stack. There's lots of libraries built on top of NumPy, but basically all numerical computing, or almost all numerical computing in Python, is built on top of NumPy as a foundation. And one of the things I want to emphasize today is that using NumPy effectively requires changing the way that you think about and solve problems. So the way that you might think about solving a problem in normal Python is not necessarily going to translate into an efficient or idiomatic or sort of correct NumPy solution. And a lot of what we're going to focus on today is sort of understanding why that's the case and how to use the tools that NumPy provides for you so that you can actually take advantage of what it's doing. So before we get started with sort of the main content of the lecture, I want to make sure everyone is kind of comfortable with the Jupyter notebook environment and is comfortable with finding functions and reading documentation. A lot of the exercises, I'm going to give you hints towards the functions you're going to need to use, or I'm going to give you examples, but then for some of the later exercises, you're going to have to find little pieces of functionality that you want. So the first exercise that we're going to do is actually a warm-up, and it's going to teach you how to find functions and read documentation from inside of Jupyter. So if you're on the exercises or if you've got the repo running locally, you're going to want to pop out to the notebooks and open up the Finding Functions and Documentation notebook in Jupyter. And what this notebook is going to talk about is how to use NumPy to sort of do keyword searches to find different pieces of functions. I'm going to do a quick demo of how Jupyter works. So all these lectures and all these tutorials or all these exercises are running in Jupyter, which is a browser-based Python code execution environment. The way this actually works is you type something in the browser, and then it's going to send a message to a Python process running on a server somewhere that's actually going to execute your code. And so the important things you need to know for this tutorial is that there are two kinds of cells. There's markdown cells, which are these ones that are sort of just like HTML prose here. If you accidentally click on one, it's going to turn like this, and it's going to look like text. If you hit Shift-Enter, that's going to execute the cell. So executing a cell in Markdown means rendering it. If you have a Python cell, which you can identify by having this little sort of in square bracket, I'm going to make this a little larger for the people in the back so you can see. If you have this little in square bracket, then there's two ways that you can execute a cell. You can either hit Shift-Enter, and that's going to say execute the cell and then navigate to the next cell. So that's useful if you're just trying to sort of execute a notebook in sequence and navigate the whole thing. The other way to execute a cell is if you hold Control and hit Enter, then that'll execute the cell and leave you in place. And that's often useful if you're iterating on a cell, you're writing a function, you're trying to test it out. So those are the two main things. So I'm actually going to turn the mic off and let people sort of browse through this notebook for about 5 minutes and just sort of get comfortable and get familiar with using the notebook and finding things. If anybody has any questions, I'm going to be walking around. Feel free to ask me. Also, I want to introduce Anna and Eric, who are here helping out. They're also going to be walking around. They're both super knowledgeable about all the things we're going to talk about today. So if you have any questions and I'm not available for whatever reason, you can grab one of them. I'm going to put this back on the slides page so people can see. This is a static rendering. Sort of assign some variable and then show you the variable. And that's the reason you'll just see like the naked variable there is so that I can print the expression. Bigger when I get there. Hello, hello, hello. Hello? We definitely got audio there, right? All right, cool. All right, so people, you can feel free to keep sort of noodling on that notebook, but we're going to get into the main lectures here. So, like I said, I'm Scott Sanderson. I build sort of tools for quants to do algorithmic trading in the browser in Python. We talked about NumPy, talked about warming up. So before we get into sort of talking about NumPy proper, I want to sort of talk about why we need NumPy and why numerical programming using sort of what Python provides for you out of the box tends not to sort of work very well, at least tends not to be performant. So in order to do that, I'm going to talk a little bit just about Python's built-in data structures. In particular, we're going to talk about lists. So here I've got a Python list. Is this legible for people in the back? Cool. So I've got a list. This is sort of a vanilla Python list. One thing that's interesting about this list is that I have values of different types in this list, right? So I have an integer. I have the integer 1. I have the string 2. I have a floating point value 3. Then I've got another integer. Then I've got the complex number 5. This is actually 5i. And then I've got another string 6. So Python is sort of perfectly happy to let us put differently typed objects in arrays or in lists and dictionaries, and that's sort of a core part of how Python works, is that it's dynamically typed. We can mix and match and put whatever kinds of values we want wherever we want. Lists are primarily sort of sequenced containers. So the operation you do most often on lists is indexing, right? So I can get the first element from a list by doing L bracket 0. I can get the second element out of a list by doing L bracket 1. And one thing that's maybe a little bit less commonly known is that lists support negative indexing. So if I do L bracket -1, that says get me the element from the end of the list. And if I do L bracket -2, that says give me the second to last element from the list. So if I execute that, we can see the last element, I get the string 6. Second to last element, I get the string 5 as a complex number. Or rather, I just get 5 as a complex number. Lists also support this convenient slicing syntax. So if I want to say get all values between index I and index j, the way that we say that is we do L bracket I colon j. So if I do L bracket 1 colon 3, that says give me the elements from 1 to 3, not inclusive of 3. So this gives me elements at indices 1 and 2. So here I do L bracket 1 colon 3, and I get the string 2 and 3 as a float. Oops. Shorthands for that, often you want everything up to a point or everything after a point. So if you omit either of those indices, it's equivalent to putting either 0 or the end of the list. So L bracket colon 3 gives me the first 3. L bracket 3 colon gives me everything after 3. Also, maybe a little less well known is that there's actually a third parameter to that slicing syntax, which is a step. So if I do L bracket sort of start, stop, step, that says start at the start, go until the stop, and proceed in increments of the step. So if I do 1 colon 2 or 1 colon 7 colon 2, it says start at index 1, then jump to index 3, then jump to index 5, and we would jump to index 7, but we're not inclusive of that right endpoint, so we won't include it. So this gives me B, D, and F out of this list. So we've got here, here, and here. Another important feature of lists is they're mutable, so I can append an element to a list efficiently, and I can remove an element from the back of a list. So unlike some of the other data structures we're going to see today, lists sort of allow us to freely change their shape, right? So before I've got a list 1, 2, 3, 4, 5, then I append 6. After that, I've got 1, 2, 3, 4, 5, 6. And again, we'll notice that we not only do we append a value, we appended a value of a different type than the other values in the list. And finally, one thing that I want to highlight is that Python has this comprehension syntax, which is sort of most commonly used for mapping an expression over a list, right? I've got a list of values, and I want to compute the same function or the same expression on every element in that list. And Python actually has a built-in syntax for doing that. So I can say x times 2 for x and L, and that says basically what the English says. So it's going to compute x times 2 for every element in the list. So I started with 1, 2, 3, 4, 5. I get 2, 4, 5, or 2, 4, 6, 8, 10. So quick review of that review. Lists are zero-indexed sequences of values. We can hold values of different types in a single list. They support this slicing syntax with this start, stop, step style. It is efficient to append or remove from the end of a list. We can also insert to the front or into the middle of a list. That's less efficient, but it is still a supported operation. And finally, we have this comprehension syntax to sort of map an expression over a list. So that's great, right? We like lists. Lists are sort of this great data structure that we use all the time in Python. So what's the problem with lists and the problem with Python built-ins when we want to use them for sort of heavy-duty numerical computing? So say we want to represent sort of a matrix and do matrix algebra, right? So one way that we could represent a matrix in pure Python is to just have a list of lists, right? So I've got my matrix A, which is a list of length 4 containing lists of length 3, and we could think of this as though it were sort of a 4x3 matrix. And the same thing I can do with this B. I've got my 2x4 matrix here. So one thing that might be an issue here is that an invariant we probably want to enforce on this matrix is that it has a value at every column and every row. But because lists are mutable and because they sort of allow us to hold whatever we want, we could very easily just remove a value from one of these lists, right? And Python's none the wiser, it doesn't know anything about that. We could put a data structure that wraps around this and tries to prevent us from doing this, but fundamentally it's sort of hard in Python to preserve the shape invariants that we want to provide. So that's one reason why, even ignoring any performance concerns, why we might feel like lists aren't the right data structure for this. Another thing is that Python's built-ins, if we want to do numerical programming, get pretty verbose pretty quickly. So here's an example of how you might write a matrix multiply algorithm in Python, or in pure Python. And you shouldn't read, if you can read this and you immediately understand and believe that it's correct, I'll be a little bit surprised. I read this sort of I feel kind of icky here. We've got nested for loops, and one of the things in the Zen of Python is flat is better than nested. So already we should feel a little icky about ourselves, and normally in Python, we like to just iterate over the values from things. We don't like to iterate over indices and then index in them. So something about this sort of feels like it's not very Pythonic, right? So if I see that code, this is kind of how I feel reading this as a Python programmer. It's just ugh. But maybe that's fine. Readability isn't the only thing. Readability counts, but it's not the only thing that counts. So what we really probably care about a lot of times if we're doing heavy-duty numerical computing is how fast is it. So one thing we can use to try to measure that is Jupyter provides this built-in % time magic that you can use to run a cell and tell you how long it took. And I didn't execute that previous cell. I promise you that matrix multiply works. So if we ran this, we see that for those relatively two small matrices, it took 27 microseconds to execute that. And I don't know about you, I don't really have a sense of whether that's good or that's bad or how we should feel about that. So one way we could try to answer that question is to try to get a sense of how this scales as we make the matrices larger. So here I've got a function to just generate a random matrix of shape m by n in that sort of list of lists format here. So if I make a random matrix that's 2 by 3, I get something like this. If I give it a 3 by 2, I get something like this. And we're just going to time how long it takes to do a matmul on matrices of different sizes. So I'm going to start on one a little bit smaller. So with 100 by 100 times 100 by 100, this takes about 1.6 or 0.16 seconds on my machine. If I up this to sort of 300 by 100 and 100 by 300, now it starts to spin for a second. Now we're up to 1.4 seconds already. So already we should start sort of feeling a little queasy. 1.4 seconds is a long time in computer time. And if we update this to say 600, we're going to hang out for a bit. So 5 seconds, right? So this is not scaling well for us. And if we, for the kinds of applications that I work on, we're usually looking at arrays on the order of thousands by thousands. So very clearly this algorithm is not going to scale to anything sort of approaching reasonable for the use cases we want to hit. But maybe that's just as good as we can do, right? Maybe sort of numerical computing is just this fundamentally hard thing, and there's no way to go any faster than Python can do that. So one way we could try to measure that is to try to take a little bit of a simple case. So matrices, we could actually do better algorithms than what I just showed there. But sort of we just want something that benchmarks kind of our core ability to multiply things and add things really fast. We might do something like a dot product. And if you sort of don't remember your linear algebra, dot product is just taking two vectors, multiplying them element-wise, and then summing up all those products. So Python can actually express a dot product sort of relatively nicely, right? So I'm going to do sum of x times y for x comma y in zip x's and y's. And we're going to compare that to Fortran, actually. So Fortran is kind of the gold standard for high-performance numerical computing. It's a language that's essentially designed to be really, really fast at things like dot products. So one thing we immediately notice with Fortran is that it's a lot more verbose, right? We've got all this kind of boilerplate going around with, double precision intent in X's with some weird sort of call of a colon here. We've got the same thing for Y's. We've got this intent out thing. But although if we actually ignore kind of the boilerplate at the top of this function, the logic here is pretty readable and pretty pleasant, right? So one thing we notice is that what this parentheses colon thing says is that X's and Y's are arrays here. And we'll notice that array times array is actually a built-in primitive in Fortran. So it has a native notion of what it means to multiply an array by array. And it turns out what it means is that element-wise multiplication, which is precisely what we want for a dot product. And it also just has a built-in sum function to sum over those values. So we're going to use f2py, which is a library for sort of building Fortran and then creating Python bindings for it. This probably isn't how you probably don't want to use the notebook to run your Fortran code like this, but the things that this is built on top of are basically how you would sort of bind Fortran code in Python. And a little bit of sort of spoiler here. So we're going to have some list data, right, which is just going to be float I for I in a big list. And then we're going to convert that to a numpy array, because that's actually all the Fortran code's going to understand. So we're going to pretend that we didn't see that part until a little bit later. And then the question is, right, is how fast is this? So if I want to do this dot product in Python, that actually runs pretty quickly, right? That took about 16 milliseconds. And now if I run the Fortran code, that's 172 microseconds. So we're about a factor of 10 slower than Fortran here. Sorry, we're about a factor of 100 slower than Fortran. So Fortran's quite a lot faster than us. And now sort of our question is why? Right, so when we're writing numerical programming code in Python, this is kind of how I feel. I think we're just sort of like slowly multiplying matrices. So the question we should have here is, right, why is the Python version so much slower, right? What is it about Fortran that allows it to, do this dot product 100 times faster than Python when the algorithms are essentially the same? So one thing that makes Fortran faster, or rather makes Python slower here, is the fact that Python's dynamically typed, right? So here's sort of a slight variation on that dot product. I just have multiply element-wise. So I'm taking X's and Y's, I'm multiplying them together. I'm not doing any sum afterwards. And I'm going to call multiply element-wise with some interesting inputs. So my first input's pretty reasonable, right? It's just 1, 2, 3, 4 as integers. But then my second input has a bunch of differently typed things here, right? So I've got the integer value 1. But then I've got 2 as a complex number. I've got 3 as a floating point value. And then maybe most worryingly or most surprisingly, I've got 4 as a string. And your immediate reaction to that might be like, does that even work? Like, should that raise an error? You might be surprised that integer times string is even well defined in Python. It turns out what that means in Python is to sort of concatenate that string with itself the number of times equal to the integer. Right, so we get back here, we get 4 different values of 4 different types in our string, in our list when we do that. So we have an integer, we've got a complex number, we've got a float, and we've got 4, 4, 4, 4. And if we ask Python what are the types of all those things, it'll tell us you've got an int and a complex and a float and a string. And if we think about what must have happened here, Python had to do something pretty interesting in order to compute this result, because it essentially did a different thing for the multiplication for each value in that list, right? Every type in my second list here has a different notion of what it means to multiply that type by something else. And Python, because of the way it works, can't know that ahead of time. So what that means is that every value in Python essentially carrying around what its personal sort of definition, what its sort of personal relationship to multiplication is. And when Python needs to multiply something together, it's going to say, hey, value that I'm about to multiply, what does it mean to multiply you? Right? How do I multiply you? And then it's going to do that multiplication. And it's going to do that every single time that it does anything in our list. So every time we do this multiplication, Python has to look at both of the values it's about to multiply, figure out what it means to multiply those two values, find the actual definition of that function, and then apply that multiplication. And it turns out that when we're multiplying thousands and thousands of things or adding thousands and thousands of things, the overhead of sort of figuring out what multiplication should mean for you is going to totally dominate the cost of the relatively cheap thing we actually wanted to do, which is just multiply 2 integers or multiply 2 floats. The other thing that slows down Python here is kind of this related concept, but it's the fact that Python is an interpreted language, right? So I can take Python and there's no, in many languages, there's a compile step between writing your code and actually executing your code, where you write some Fortran or you write some C, And before you actually run that on a real processor anywhere, you're going to run it through a program that translates your code into a format that your sort of CPU processor actually knows how to execute, or maybe to some other efficient virtual machine knows how to execute. That does happen in Python as well. So when we take some source code, the first thing that Python does is compile it into this format called bytecode, right? So if I sort of use this compile built-in to evaluate a string of code and compile it into bytecode, I get back this code object, so I can actually, as a Python value, carry around sort of instructions that are the definition of how to execute some code. And then I can actually see sort of what the instructions are that Python generated there. So if I use the dis module, which is the disassembly module, I can actually get it to print exactly what the sequence of instructions are that it's going to run when it does this A plus B times C. So we can see it's going to load the value A, it's going to load the name B, it's going to load the name C, it's going to do a binary multiply instruction, which is what's actually going to do all that dispatching that we just talked about. And then it's going to do a binary add instruction, which is going to do the same dispatching for the add. So in addition to the sort of expensiveness of doing the binary add and the binary multiply, there's also, at the core of the Python interpreter, there's essentially a big switch case sort of sitting in a loop here that's reading each one of these instructions one at a time and saying, okay, now I need to execute a load name instruction. I need to jump to the definition of that instruction and execute it. All right, I need to do another load name. I need to do another load name. I need to do a binary multiply. And so there's a big loop that's just sort of sitting and reading these instructions and executing them one at a time. And again, the overhead of sort of like having to figure out what it is that you need to do next turns out to add a significant overhead to the work that we need to do, especially when we're doing something like numerical computing, where we actually expect to essentially be doing the same operation over and over, right? So we're going to do the same thing just like repeatedly tons of times in a loop, and we know that as programmers, but Python doesn't know that. Python is just going to sort of keep saying on every single time, oh, this might be the instruction that's not a multiply anymore. This might be the instruction that's not an add anymore. And it has to sort of know, it has no way to know that's not the case. So to review what we just talked about, right, the reason the Python version is so slow is primarily two reasons. So one is that dynamic typing means that every single operation that we do requires dispatching on the input type to figure out what the definition of the operation we want to do is for that type. And the other thing is that having an interpreter means that every instruction has to be fetched and dispatched in runtime. And again, what that means is when we're doing the same thing over and over in a loop, the overhead of figuring out that we still just need to do the same thing turns out to dominate our runtime. There's some other overheads that are sort of smaller that I'm not going to talk about here. So one is Python supports arbitrary sized integers, which means they have to have a more interesting representation than what something like Fortran or C would use. And it also supports reference counted garbage collection, which means that essentially anytime you touch a Python object, you have to like increment a counter, and then when you finish with it, you have to decrement a counter. And again, that's sort of overhead that when you're doing lots and lots of really cheap operations, those overheads turn out to matter a lot. So this is a quote from Jake Vanderplas's PyCon talk in 2015. It's one of my favorite talks about NumPy and is sort of part of what inspired this tutorial. So Jake says, this is the paradox that we have to work with when we're doing scientific or numerically intensive Python. What makes Python fast for development, this high-level, interpreted, dynamically typed aspect of the language, is precisely what makes it slow for code execution. So this is sort of the challenge that we find ourselves in when we want to do high-performance numerical computing in Python, is how do we solve this problem? So what do we do, right? What's the answer to this? So one answer is to not use Python for this, right? We can run away. We can use Fortran, we can use C, there are other languages that are designed for this, and maybe we just say, Python doesn't need to be the best language at everything. We can use other languages for what they're good at, and we can use Python for Python. But we're here, we're at PyCon, so we probably like Python. We'd like to find a way to do this work in Python. So another option is to just accept our fate and just accept that our code is going to be slow and just sort of say, this is fine, right? This is how the world is. And we might hope that Moore's law is eventually going to sort of save us and make it so that it doesn't matter that our code is 100 times slower than Fortran because computers are so fast that no one cares. It seems unlikely that that's going to happen. And even if it were, we probably still would be interested in figuring out ways to make it faster because like power efficiency is starting to matter more and more. So I think neither of those are really acceptable options, at least for this audience. So maybe we can step back and think about what's the core problem that we're running into, right? So the core problem, again, is that normal Python is slow for numerical computation because it's doing dynamic dispatch on every operation we perform. And that's both sort of at the level of like binary adds or binary multiplies, as well as at the level of doing this instruction dispatch. And that's bad for numerical computing because most of the time when we're doing numerical things, we have these big arrays of numbers, and we just want to do the same thing over and over really, really fast, right? If I've got a dot product between two big vectors, I just want to be able to sort of crush through and do as many multiplications, as many additions as I can. When we want to do the same thing over and over in a loop, having this sort of interpreted dynamic dispatch is sort of hurting us. And so the question is, if we know that we don't need Python's dynamicism, can we find a way to not pay for it, or at least to not pay much for it? And so here's the big idea. This is essentially the thing that makes Python an effective language for numerical computing is, can we find a way to do that dispatch once per operation we want to do instead of once per element in our arrays, right? The thing that's really killing us is we have these really big arrays. Semantically, we just want to sort of add things together or like element-wise, but we have to do all this work per element. So if we can figure out a way to just do this work sort of once per array instead of once per element, then we can do a lot better. And this is where NumPy comes in. So NumPy is a language and sort of, or is a Python module. It's a little bit of an interesting module in that large parts of it are written in C, but when you're using it from Python, it sort of looks and feels and behaves just like a normal Python module, at least once you have it installed. And the core data structure that NumPy provides, it provides a lot of sort of utilities and functions and helper methods for doing things, but really sort of the core guts of NumPy is this ndarray type, right? And the way you normally construct an array is you call this np.array function. And so we can see that I'm calling np.array. I'm passing a list of values 1, 2, 3, 4, 5, 6, 7, 8. And there's a couple features of this array that I want to sort of draw your attention to and contrast with what we just talked about with lists before. So one thing to notice is that there's this dtype attribute that says this array isn't sort of a generic array, it's an array of int64. So this array can only hold values of a specific sort of machine interpretable type. And that's gonna be important for how we get good performance. The other thing I want to draw your attention to is that the array has a notion of a shape. So the simplest shape you can have is a one-dimensional array, in which case your shape is a length 1 tuple of just the length of that dimension. But we can have more interesting shapes. So for example, if I take this array and call .reshape, say I reshape this into a 4x2 array, so now I've got sort of a column vector here, right? I'm going to put a new line there so you can read that a little better, right? So now I've actually got a two-dimensional array, which is going to print for us as though it were a list of lists. Under the hood, it's not actually sort of represented as a list of lists, but you can think about it semantically as though it were kind of that nested list of lists that we saw before. And I can reshape this, to 2x4, or I can even reshape this to more than 2 dimensions. So NumPy provides these sort of arbitrary n-dimensional arrays. And we'll see what that dimensionality buys us a little bit later in this tutorial. And then the other sort of really important thing that NumPy provides us, it provides us these operations that vectorize over the array. So I can say, in the same way that we saw with Fortran, where I could say sort of data plus data, I'm going to make this back a little bit smaller to say 4x2 again, 2x4. I'm going to get indices mixed up at some point today quite a bit. Right, so I can say data plus data here, and in the same way we saw that Fortran had sort of a native notion of what it means to add an array or multiply an array to itself, NumPy has a native notion of what it means to add an array or multiply an array by itself. So if I do data plus data, what's going to happen is it's going to sort of add the elements at the same location. So I did 1 plus 1 and got 2 here. I did 2 plus 2 and I got 4 here. 3 plus 3 gave me 6 here, et cetera, right? So I sort of took the arrays, lined them up, and then sort of did the binary operator between each value here. And this works for basically any of your numerical operations. If I do like data times data, I'm going to multiply them element-wise. If I do data divided by data, I'm just going to get 1 everywhere. Data mod data is going to give me 0. You can do more interesting things like shifts. Basically, any of the binary operators that Python supports, if it makes sense for a number, it probably makes sense for a NumPy array. And so the thought here, right, is that if we can do this dispatching once per array, then once we know that I have 2 arrays of int64s and they're the same shape and I know how to multiply them together, then what I can do is instead of doing that dispatching over and over in a Python loop, I can drop into sort of highly optimized C, or I can even in some cases call into sort of the Fortran code that's designed to do linear algebra, and it's been around since the 70s and is really, really optimized. So with NumPy, like the simplest way I could do a dot product here would be to do data times data dot sum. And that's going to sort of multiply the 2 data arrays together, give me a new array that's all the products, and then I'm going to sum it to aggregate across all those values. And we can see we're already quite a bit faster than our previous examples. Turns out you can actually do even faster than this. So one thing we notice is that this is actually going to sort of materialize a whole new array, even though we only care about the sum. So NumPy provides a built-in dot product operation that can do better because it doesn't have to hold those intermediate values in memory. And data dot, dot wants to be matrix multiply on 2D arrays. So I'm gonna drop back to a 1D array. There we go. Yeah, so yeah, so we're actually about the same here, which I'm a little surprised by. But so, yes, that was added for NumPy, in fact. So yeah, so the question was, does the Python matrix multiply operator here allows you to do matrix multiplication as a binary operator? We're gonna see that a little bit later, but yes, that was actually added specifically so that NumPy didn't have to have this sort of duality where it's in some context you wanted it to multiply to mean sort of element-wise multiplication, and in another context you wanted it to mean matrix multiplication. So anyway, so we've got our data times data, we've got our data dot data, and then we've got our fortran dot product. And I'm actually going to make this a little bit bigger so that we can get a more interesting example. Oops. Uh-oh. Did I get stuck here? Hang on one second. Sorry about that. There we go. So I'm actually going to use the array data that we used before for the bigger dot products. And we'll do that up here as well. All right, so before I think we were at like 161 milliseconds for pure Python on this, and now we're down to quite a bit faster than that. And then the pure one can do even better than that. And if we look at sort of NumPy's native dot, this is really what I want you to see. So NumPy's native dot takes about 300 microseconds here, and Fortran's takes about 233 microseconds. So we're not quite at Fortran levels, but we're kind of within shouting distance of it, right? We went from being 100 times slower to being about 20% slower, and that difference would actually get closer if we made this array larger. There's still a little bit of overhead from doing that initial level of dispatching that the Fortran code doesn't necessarily have to do. But we're now sort of at the point where we're sort of within shouting distance, and we could probably make a reasonable argument that the productivity gains we get from using Python might outweigh the cost of developing software in Fortran. So we just talked about sort of the benefits we get from NumPy. I want to talk about what we trade away from, right? Like sort of nothing in software is for free, and so anytime someone has given you something, you should ask, well, what have you taken away from me in order to do that? And whether or not you care about what was taken away. So one thing that's been taken away from us is we can no longer put arbitrary values in this array, right? So we saw before that it was an array of d-type int64. And so what that means is if I try to write a string into it, it's going to error. It's going to error in what I think is kind of an unfortunate way, which is that it's going to error trying to coerce this string into an integer. So the error here is saying that foo is not a valid integer literal. I don't know that that's the design decision that I, or maybe even the NumPy folks would make today, but that's sort of how it works. If I put some sort of like truly unpleasant object in here, then you still get essentially the same thing. So basically what's going to happen is if I try to write something into an integer array, NumPy is going to try to coerce it to an int. And if it fails to do that, then it's going to barf and say, I don't know what you wanted me to do with that. So one thing that we can't do with this is we can't put other values. Oftentimes that's actually a benefit for us. Like if we didn't mean to put strings in our big matrix multiply array, and I suggest that it's probably not a good idea to want to put strings in your big matrix multiply array, then if anything, this is actually probably catching bugs for us rather than sort of imposing an unpleasant restriction on us. The other thing that we can't do with this array, which would be useful in some other cases, is we can't change its size anymore, at least without making a copy of it. So if I do, there's no append operation on an array. There's no way to sort of efficiently change the shape or the number of elements in the array. So we saw that we can reshape an array, right? I took a length 8 array and reshaped it to 2 by 4 or 4 by 2 or 2 by 2 by 2. But importantly, those all sort of kept the number of values in the array the same. And what I can't do is change the number of values. Right, so we can reshape things, but we can't sort of append or change things. We can concatenate arrays, but that's going to create a new array, for example. So to review sort of basics of NumPy arrays, they're fixed type. They're size immutable, so we can't sort of change their size at will. They're multi-dimensional. We saw I can have 2D arrays, I can have 3D arrays. Most of the talk today, we're going to use 2D arrays because they're sort of visually easier to see, but there's lots of use cases where sort of higher dimensional arrays are very valuable, and we will see a couple of those today. And NumPy arrays are fast, most importantly, right? Where they're within shouting distance of fortran, which is kind of the gold standard for what we want to do. And then the asterisk on fast is that they're fast if you use them correctly, right? So we talked about the reason NumPy arrays can be fast is that they allow us to define these operations sort of at the array level. And because we can do them at the array level, we don't have to pay the overhead of all the dynamic dispatch that's slowing down our Python. So a common failure mode that I see when people use NumPy is they hear, oh, NumPy is really fast for numerical computing. So they swap out all their lists with NumPy arrays, and then they're still just writing for loops over the NumPy arrays and doing the same algorithm that they wanted to do because they heard NumPy was faster. And it turns out your code will actually be a lot slower if you do that because NumPy is designed to be really good at these array by array things, and so it's actually much slower often to iterate over a NumPy array than it would be to iterate over a Python list. So if you've got some algorithm that you're using lists for and it's too slow and you want to switch it to NumPy, you probably actually sort of need to rethink about and restructure your algorithm in order to actually take advantage of NumPy. And so what we're going to talk about for most of today is what those restructurings or what those algorithms might look like. So with that, we're going to drop into another exercise, and this exercise is going to be about measuring performance of NumPy arrays versus or actually, sorry, that's the wrong slide. So the next exercise is going to be about creating and reshaping arrays, and there's an exercise at the end that's about measuring performance. So actually, before we dig into the exercise, I want to show you this. I rearranged some of these slides, and that slide should have been 2 slides later. So the things that I want to talk about before we get into that. So the rest of this talk is basically going to be broken down into 5 sections that are each going to be talking to you about different tools that NumPy provides to allow you to do the things you want to do. So the 5 things we're going to talk about today are creating and reshaping arrays. So before we do anything else, we need to be able to make arrays. And then we're going to talk about ufuncs or universal functions, which are these functions that can be sort of applied across all the elements of an array, regardless of its shape. Then we're going to talk about different ways that we can sort of select and slice and dice and get values out of our NumPy arrays. We're going to talk about reductions, which are various ways that we can sort of summarize an axis of an array. So things like mean, median, sum, max, and maybe some more interesting ones. And then finally, we're going to talk about NumPy's broadcasting system, which is the way that NumPy allows you to take arrays that aren't exactly the same shape, but are compatible in some sense that we'll talk about more in detail there. And broadcasting, as it turns out, is going to be kind of the glue that takes all these tools and really makes them work seamlessly together and makes them work well. And taken together, I think these operations sort of form a really expressive toolbox that we can use to solve a pretty diverse set of problems. Before we do any of those operations, obviously we need some arrays to work with. So depending on what you're doing, if you're doing sort of real work, usually your data is going to come from some external data source. But there are a bunch of helpful things that you can do to actually create arrays sort of afresh from scratch. So the simplest one is this numpy.ndarray function that I showed before. And you pass that a Python list or maybe a Python list of lists if it's the right shape and has the right values. And that'll take those Python objects and convert it into NumPy's internal representation. Another commonly used function is np.arange, which is the NumPy equivalent of the Python range function. So you say, give me a range from start, stop, step, and it'll give you an array containing integer values, which are sort of the indices from start, stop, incremented by step. np.linspace, right, I have a slide here. Yeah, so right, arange lets us make sort of, it's like range, but with an array. np.linspace, I do sort of like -1, 1, 10. It's going to give me 10 sort of evenly spaced samples from -1 to 1. This is often useful for things like plotting, where you want to like evaluate a function on some domain and then like plot the values out of it. np.random provides a whole bunch of different tools for generating random values with interesting distributions. This can be really useful for things like numerical simulation, where you want to generate values according to some distribution and then use them. So for example, if I do np.random.uniform, -1, 1, and say I'll do 10 values. So that's just going to generate me 10 random values between -1 and 1, and random has a whole bunch of different interesting distributions you can use. A couple other things, if you're doing matrix algebra or linear algebra, np.I and np.identity. This EYE is a pun on the capital letter I, by the way. That took me a while to realize. So that gives you a diagonal array containing, or an array of all zeros except with ones along the diagonal, which is the identity matrix in linear algebra. NumPy has a native serialization format, so if you have an array, you can say np.save and it'll sort of write a file to disk, and then you can use np.load to read it back. And then we're not going to talk too much about pandas today, but a lot of people, the way that they actually get their NumPy arrays in practice is using pandas, and particularly pandas.read CSV is sort of, if you don't have, for sort of small to medium data, CSVs are a very common format for handing around data. So we'll show a couple examples of just using CSVs in order to read numerical data into our programs. I haven't used Xarray a whole lot. I'll come talk to you after about that. I definitely have opinions on like pandas and where it's useful and where some of the pitfalls are on it. Yeah, so that was creating arrays, and then the other thing that you're going to need for the exercise we're going to do is reshaping arrays. So generally speaking, if you have an array with n cells, you can reshape it into any combination of dimensions as long as the product of those adds up to the number of elements. So I can take an array of length 16, I can reshape it to 4 by 4 or 2 by 8 or 2 by 2 by 2 by 2. Right, these all sort of work. And finally, a common operation that's not quite reshaping, but it's pretty similar in a lot of ways, is transposing an array. So if I have a two-dimensional array, and a common thing, especially in linear algebra, is you want to sort of like rotate it around like a 45-degree angle. So here I've got a 3 by 4 array, which is data, and then if I do data.t, it's actually so common to do this that there's just a property on arrays called transpose, or called .t. Sorry? Yeah, you can think of it that way. It's going to take your shape and like rotate it 90 degrees, except that the things get flipped around the axis. Okay, so with that, we're going to go into the exercise on creating and reshaping arrays, as well as a little bit on measuring performance. Doing these exercises, if you have questions about sort of the previous lecture section or about the exercises, feel free to flag me down while I'm walking around. this is locally and you're getting errors about fortran magic not being installed, you can probably just comment out those cells and continue working. I think I forgot to include that in the dependency list that I sent out. That one's mostly just a gimmick because I think it's cool. Hint for people, if you get to the one about how to make an array in descending order, check out the docs for arange. There's a third argument to it that you can use cleverly to get a reversed array. 3 more minutes on this exercise, and then we're going to move on so we can get a section in before the break. I will say I don't necessarily expect everyone to finish every single exercise in any of these sections. So, you can feel free to sort of review these. They'll be posted afterwards online along with solutions. And also, during the breaks or during another exercise, you want to go back to a previous exercise, feel free to do that as well. But I've tried to put enough content into all these so even folks who are more advanced and have used NumPy before will have something to do, which means if you're brand new to NumPy, I definitely don't expect you to make it through all the content. Back into the lectures. We've got about 10 minutes before the break. So we're going to do one more section here, and then we'll break. People can go off to get sort of whatever food or water or drink they want, and then when you come back, we'll go into the next set of exercises. So we'll have a little more flexible time for that one. Cool. So we just talked about creating and reshaping arrays. So now we know kind of how to construct arrays, how to get arrays into our program. The next obvious question is, well, what do we want to do with those arrays? And so the most common thing that we're going to want to do with those arrays is sort of evaluate functions or run expressions that are kind of element-wise over the arrays. So NumPy provides a whole bunch of functions that are NumPy aware that know how to do this. And they're called universal functions, or ufuncs for short. And ufuncs are basically functions that can be applied across one or more arrays as long as those arrays are the same shape. And then what it can do is the thing we saw with plus or multiply before, where it'll sort of do them element-wise across each other. If you've used NumPy before a lot, you may know that what I just said isn't quite true. They don't have to be exactly the same shape. But for the purposes of this section of the tutorial, we're going to assume that they have to be exactly the same shape, and then later we'll see how to relax that restriction. So ufuncs come in two main varieties. We have what are called unary ufuncs, which just sort of a function that applies to an argument and maps some function over that. And then we have binary ufuncs, which are going to apply a two-argument function over sort of the corresponding elements of two arrays. So again, I'm just going to sort of generate some data here. So the unary functions are things like, say, np.square root. This is going to say, take my array, calculate the square root of every value in the array. I'll make that a little bit smaller. Is that still legible for people in the back? Okay. Make it a little bigger. It's going to wrap a little bit, but it's okay. I'm not going to try to mess with that right now. Right, so square root's just going to take our array, calculate the square root of everything. Other sort of similar functions, np.log is going to calculate the natural logarithm of every element in the array. And np.sine is going to calculate the sine of every element in the array. So basically any kind of like mathematical function you can think of, square root, power, logarithm, any kind of trigonometric function you can find here. NumPy sort of limits itself to the basics. If you need something sort of more exotic that fits this shape, good odds you can find it in SciPy, which is kind of NumPy's sister package, which uses NumPy arrays and sort of works with NumPy arrays and implements all kinds of tools for doing scientific computing on the arrays. So in particular, scipy.special contains all kinds of weird functions for doing like statistical work or for like whatever weird like physics distribution you want. So if you're doing something that's a standard somewhere in a scientific field, reasonable odds it's in SciPy somewhere. And then finally, we've got sort of these binary functions. So we can do like data plus data. And we can see that, right, we already saw an example of how this works. We can do data, times data. We can do data divided by data. So basically, all of the, Python's built-in binary operators are binary ufuncs in the NumPy case. I'm going to just copy this up and then slide it back down so people can see. Another kind of operation that can be vectorized this way that's maybe a little more surprising to Python people is comparison operators. So here I'm doing data mod 3, right? And that's just going to give me every element in the array modulo 3. So I'm going to sort of be 0, 1, 2, 0, 1, 2, 0, 1, 2. And then NumPy actually overrides what it means to do an equality comparison on an array. So normally if you have two Python objects and you do equal, equal, you expect to get a Boolean value back that tells you whether or not the values are equal. Turns out NumPy or Python allows you to override how the equality operator works, and you don't have to return a Boolean. So for example, I can do data mod 3 equals 0, and what that's going to do is say compare 0 element-wise to each element of my array, and tell me is that element equal to 0. So this is an easy way for me to say, give me all the locations, or tell me all the locations where the array is divisible by 3. And there's a bunch of different ways that these Boolean arrays turn out to be useful in various contexts. And we're going to see some of those in a little bit. And so you can pretty easily, using these chained operators, you can build up pretty sophisticated expressions here, right? So here is me saying, all right, now I actually want all the locations in my array that are divisible by 6, which of course, a better way to do that would be just data mod 6 equals 0. But one way we could build that is to say, give me all the locations that are divisible by 2, which is what this expression is going to do, and then use ampersand, which is and, right? So that's going to say, give me all the places where that array is both true, where it's true in both of the expressions on either side. Right, so this is going to say, give me all the places where it's divisible by 2 and all the places where it's divisible by 3. And what that's going to give me is all the places where it's divisible by 6. And I could switch this to, say, the pipe operator, and now I get all the places where it's divisible by 2 or 3. So now we get this pattern of like false, true, true, false, true, true, false, true, true. Finally, this got mentioned earlier, but as of Python 3.5, the at operator is a matrix multiply, right? So if I've got data here is a 2D array, I can matrix multiply that array by its transpose, so I can do data at data.t, and I get a 3x3 array back, which is the result of that matrix multiplication. And if I did, for example, data.t at data, I'd get a 5x5 matrix back instead. So that's sort of the main ideas behind ufuncs. One thing to know is that all those binary operators actually have sort of a function version as well. So like if you're writing some higher order function, say, or there's some other reasons why you might want to use these, but so like plus and minus and times and divide, there's functions that do those, which is like np.add, np.subtract, np.multiply, np.divide. A common reason to use these is that these all take an out parameter. So if you're doing really high performance things, you often care about memory allocations. Those turn out to be your bottlenecks. And so if you're going to sort of have a whole bunch of temporary values, you can pre-allocate an array and kind of use it as like a workspace. And then you can pass that to these functions, and it'll, rather than creating a new array for you, it'll compute a value into that array. Yep. 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 Yeah, so the question is why I'm doing ampersand and pipe here. Those are usually used for bitwise operators. Why did I get true or false here? The answer is Python doesn't have an operator for distinguishing between logical and logical or. Python has the like and or keywords, but it turns out you can't override what those means because they have this weird short-circuiting semantics. So in Python on Boolean arrays, pipe and ampersand just mean sort of the logical operations. Those things on integer arrays still mean the bitwise operations. So because there's no real sense in which you'd want to do bitwise arithmetic on Boolean arrays, we kind of overload that term to mean the logical operations there. Good question. Yeah, so another reason, so we talked about one reason why you might want to use the function versions of those is they take this out parameter, which you can use to sort of more finely control how you're managing your memory. I wouldn't recommend sort of using that too heavily unless you like really know you're in a performance sensitive situation. Another reason why you might want to use those functions is all these ufunc operators are equipped with these methods that kind of give you little mini algorithms. So if I make some data here, just going to delete this so people in the back can see. And scroll that back slightly. I apologize if you can't read this super well. So the way this works is if I do np.add, right? So this is just a ufunc object, right? So it says ufunc add. Normally we don't, oops, sorry about that. Normally we don't think of methods as sort of like functions of having methods of their own, but it turns out all these ufuncs are actually a little bit more complex than just regular functions, and they come with all these extra operations. So they come with, for example, like add or accumulate and identity and reduce and some other things. So the three that I want to just sort of call your attention to, we're not going to talk about too much today, but they are useful. So one is reduce. So the way to think about reduce is it's sort of like the built-in reduce operator. And the way this works is if you have a binary operator, you can think about sort of like interleaving that binary operator between all the elements along an axis of the array. So if I'm doing this, say, along the rows, and I have add, which is plus, you can imagine, say, sort of sticking a little plus here, and a little plus here, and a little plus here, a little plus here, and then sort of squishing the array along that dimension. And so that's what reduce does. So if I do np.add.reduce of data, and I pass axis equals 1, then what I get back is an array that gives me the sums of each of these rows. And I could pass axis equals 0, and if I close my parentheses, then I get the sums of each of the columns. So that's reduce. I can do this sort of across any dimension of the array. A little bit of a fancier one is accumulate. So accumulate is like reduce in that it's going to sort of tile the binary operator between each element of the array, but instead of squishing it along some axis, it's going to sort of like cumulatively keep track of the state of that reduction. And it's going to give me back an array of the same shape, but with the intermediate values still there. So if I do add.accumulate, oops, insert, accumulate, and I want data, comma, axis equals 1. Then now what I get is not the sum, but sort of the running sum of here, right? So I had -5 is where I started, and then I go to -4, which is what I get when I add 1. -2 is what I get when I add 2. Then I go back down to -4 when I add -2, et cetera. So like a common thing where this is useful is like max for, oops, it's going to be maximum. And hopefully I can get this to go out of insert mode. I always forget how to make it do that, and I'm just going to refresh the page. Yeah. Sorry about that. Too far. Here we go. Yeah, so if I do np.add, or if I do np.maximum.accumulate, for example, it's going to give me the running max along each axis, which is often useful. Or I can do running min, running max, anything like that. So just to quickly review, ufuncs give us these efficient element-wise operations applied across one or more arrays. All the arithmetic operators you want to use are ufuncs. Any comparisons, so we talked about equal, but also greater than or less than or equal to or not equal to. Those all have those same semantics of rather than doing the comparison that you might expect, they do an element-wise comparison. If we've got Boolean values, we have these binary operators between those. And then we saw some examples of ufuncs, of unary ufuncs, which were things like square root, trig functions, transcendental functions, et cetera. We also saw these ufunc methods. We have reduce, accumulate, outer I didn't talk about. Outer lets you sort of take all the combinations of two elements in an array and run a binary function across each of those. We'll see some other ways to do similar things, so I don't focus too much on that one. And then there's these two other ones, which are at and reduce at. I've never seen them used in the wild, so I'm not going to talk about them, but if someone wants to come ask me about them later, I'm happy to talk about it. And with that, we're going to take a break to grab food outside. And when you come back, you can hop into the UFunk exercises. You guys are settling back in. Once you get there, you can start looking at the Universal Functions notebook, which is going to teach you how to use some of the tools we saw in the last section. just by themselves, they're the same. Yeah, so those are up, and then there's solutions for some of them, and I'm planning on posting those in solutions within the next day or so. Right, I'm walking around seeing some people getting toward the end of this exercise, so probably going to start back up with the lectures in 1 to 2 minutes. Hold on one sec. Cool. Yeah. NP.random has a different convention than the PyCon random. One of them includes the Yeah. I have actually written exactly that bug in code before. In here. Hopefully everyone got a chance to get at least part of the way through the ufunc exercises. So again, to sort of recap what we've talked about so far. So we talked about ways of creating arrays, both sort of from thin air as well as from sort of some data set on disk. We've talked about ufuncs, which are ways to apply mathematical functions sort of element-wise across arrays as long as they're the same shape. The next thing that I want to talk about is selections, which are different ways of sort of operating on just a subset of our data. And there's a couple different ways in which we might want to operate only on some portion of our data. So NumPy arrays essentially provide the same sort of slicing and indexing semantics as Python, or as Python lists, except they generalize it in a couple ways. So one of the ways that they generalize is they support multiple dimensions. So anything you can do on a Python list, you can do sort of along each axis of a NumPy array. Another thing they do is they allow selection by Boolean predicates. So we'll see some examples of that, but basically you can sort of compute some Boolean array and then use that to select only the values out of another array where the Boolean array is true. And then a third thing that they support is the ability to grab multiple indices at the same time. So rather than just sort of grabbing one index and one index and one index and like concatenating them, you can say natively, I want columns 1, 4, and 5, say. So just so some test data to play around. np.sine and np.cosine running from 0 to approximately pi. So the thing to see with this curve is it's for sine is it's starting at 0. It's going to go up to about 1 at the halfway point, and then it's going to go back down to 0 towards the end. And this is a one-dimensional array. It's rendering as a table here because it's wrapping. So like I said, so the most simple basic operation you might want to do is just sort of indexing with an integer value. If you have a one-dimensional array, that's just going to give you a scalar. If I have a two-dimensional array, so say I do sines.reshape for 2. Sorry, I want 5 too. Right, so now I actually have a two-dimensional array, and I index that with 0 now. So what that's going to do is actually slice off the first row of the array. Now I can do, say if I do signs 1, it'll give me the second row. And the same sort of deal with negative indexes. For example, I can do basically anything that I could do on a normal Python list, I can do here, except now when I index with a scalar on a multidimensional array, I essentially sort of chop off one dimension and take the slice just along that axis. So a good sort of mnemonic to remember is that if you have an n-dimensional array and you slice it with a scalar, you end up with an n-1 dimensional array. Whereas sort of the limiting case of that is if you have a one-dimensional array and you slice it with a scalar, you can think of a scalar as kind of a zero-dimensional array in that sense. Slicing works, again, sort of the same way as Python lists. So if I do signs bracket :3, that's going to say give me the first 3 elements of the array, and it's going to give that back to me as an array. So with a list, if I did this, I got a list back. With a NumPy array, I get this back as an array. 5: works exactly the same way. And : :2 works exactly the same way. So I can get every other element out of my array by doing : :2. So that stuff's sort of like pretty straightforward generalizations of what we've seen so far with lists. A little bit more interesting here is that we can index with Boolean arrays. So we saw in the section on ufuncs that if I did like array = 5, then that would sort of element-wise compare against 5 for everything. The thing that we often use those Boolean arrays for is to then to sort of slice out a section of another array. So for example, here I've got my array of signs, which is rendering a little awkwardly. And then I've got signs greater than 5. So again, the sine wave kind of goes up and then comes back down. So it's true in the middle and it's false on the edges. And then what I can do with that array is I can say, I can take my signs array and I can index it with the Boolean array, which I get from doing signs greater than 0.5. And one thing I want to emphasize to you is that this isn't some like fancy magic syntax, right? A lot of people look at this and think like, oh, NumPy is doing something fancy, or like pandas is doing something fancy to like let me index with these expressions. All that's happening here is that if I do signs greater than 5, I do is sorry, this would be 0.5. Is large, say. Right, so that's a perfectly good expression. We tend not to be used to thinking of like comparisons like this as like producing expressions that we're going to bind to a variable. We most often see these in sort of conditional statements. But I can just do is large here, right? And that gives me my array. And then I can do signs bracket is large. Oops, and if I don't accidentally typo that, then what I'm going to get back is the values from my array where that condition was true. So I got sort of all the middle values out of the array where the value was greater than 5. And what's nice about this is very often it lets you sort of write it kind of in line as a predicate. So I can just do signs bracket signs greater than 0.5. I don't need any of this anymore, and I get kind of the same result.
That slicing isn't necessarily continuous. So it just so happens you had only the middle
Yes.
values there, but there could be gaps in between your indexing there and where you're at.
Yeah, totally. Yeah, so like if I did like took the modulo example earlier, I could get like false true true false true true false true true things like that. Yeah, the question was in this particular case, it happened to be that all the slice that I grabbed was all sort of contiguous. But in general, right, I can have sort of an arbitrary pattern of trues and falses, and what NumPy is going to do is sort of look at the index array, figure out how many trues there are going to be, allocate an array to be that output, and then it's going to scan through the trues with the value, or scan through the booleans with the value simultaneously. And anytime it sees a true, it's going to pluck the value out and copy it into the output array.
So if you just said less than 5, you get 2 ends.
Yep, yeah, so that's a great example of this. So, right, so if I do greater than 5, I get the middle of the array. But if I do less than 5, I'm going to get kind of the bookends of the array. And so you'll notice that those weren't contiguous in the original. So that's slicing. So we've seen sort of normal Python indexing and slicing. We've seen this Boolean indexing, which is a new notion that we didn't have in lists. Another notion that Python or that NumPy has that Python lists don't have is we can grab multiple values out of an array simultaneously, right? So if I've got my array of signs here, and I index it with the list containing 0, 4, and 7, and this works with a list. It'll also work with a numpy array of integral type. Then what this says is grab the values at index 0, index 4, and index 7. So the value I get here corresponds to index 0. The value that I get here corresponds to index 4. And the value that I get here corresponds to index 7. And again, there doesn't need to be any sort of regularity here or anything like that. So like when we're slicing, what we're usually saying is like I want sort of fixed size value or fixed space value from some particular region. When we're doing indexing with Booleans or we're doing indexing with integer arrays, we're just saying I want sort of the values at these places. So you might ask, like, well, when would you want this sort of like ability to grab multiple values based on their indices at the same time? The place where this is most commonly useful is when you want to sort one array by the values out of another array. So as an example here, I've got just some unsorted data here. Right? So I've got 1, 3, 2, 12, -1, 5, 2. This is not sorted data. And there's a function called np.argsort. And what that's going to do is you call argsort of your array, and it's going to give you back an array of integers such that if you apply that array as an indexer to the original array, the array will end up sorted. Right? So what I'm going to get back is essentially a permutation on this original array. Well, you'll notice every index here appears exactly once. And what this says is that, okay, the first value in this array is the value at index 4, so that should get grabbed into the first location. And we'll see that that's -1, which is the smallest value in the array. And then the second value that you should grab should be the one from index 0, and that's 1, which is the second smallest value in the array. And et cetera, we go all the way up to the last value here is going to be the one at index 3, which is going to be this 12 here. So what this does is say it's sort of doing like an indirect sort, where instead of sorting the array in place, it's going to give you back an array such that if you used it as an indexer, it would sort the array. And so if I then take my unsorted data and I index it with these sort indices, what I get back is a sorted array. So why is this useful? So one thing that's useful for this is if I've got two arrays of the same shape and I want to sort one of them by the values of the other one. So an example here is imagine I've got prices of stocks and I've got tickers, which are like the labels for those stocks, and I want to sort the tickers in the order of the prices. So I want to sort of sort the stocks by price, right? So one way that I could do that is I can say argsort the prices to get me a permutation that would sort the prices, but then instead of applying that to the prices, I'm going to apply it to the tickers instead. So if I say tickers bracket sorter, what I end up back with is this array of labels which is sorted in the order by the prices array. So for example, D here is 5, or corresponds to 5, which was our first one. B here is, B and E are tied, actually it's 6, so the order that those come back in depends on exactly how you call argsort. And then A comes back last, for example, because that one had the highest price. So for example, if you've used like pandas and you've used like pandas like join operations, or it's like merge, or even just like sorting columns here, what it's doing under the hood is something like this, where it's sorting by the column you told it to sort by, and then it's realigning all the other things to match using that permutation array. So you can kind of just do that once and then apply it. And if you don't know what I just talked about there, that's fine. So that's sort of indexing with coordinates. I want to talk a little bit more about multidimensional arrays. So just making a 5x5 array of integers. Make it a little bit smaller. Right, so we already saw that if I slice a multidimensional array with a single scalar value, what I get back is if I slice a 2D array with a scalar, I get a 1D array. I can also sort of slice across each dimension independently. So if I do data bracket :2, :2, it's going to apply the first slice to the rows. So that's going to say, give me the first 2 rows. And it's going to apply the second indexer to the column. So it's going to say, also only give me the first 2 columns. So when I apply this, what I'm going to get back is sort of the top left square of the array, right? We expect to kind of get these 4 values back. And in fact, that is what we get when we run this. And what's interesting here is we can mix and match these different kinds of indexing, right? So just delete this to give us a little more space. Actually delete it. There we go. Right, so I can mix and match these different kinds of indexing. So if I say data bracket :2, that says give me just the first 2 rows. But then I can use the coordinate indexing to say, give me the first and the last columns here. And so now what I'm going to end up with is these 2 values and then these 2 values. So you can kind of mix and match these different kinds of indexing. And I could also, for example, index this with like a Boolean array and say I evaluated some predicate like array or data bracket 0 mod, say I'll just do, mod 2 greater than or equal 0. And I think I need parens here because how the precedence works. Right, so now I get sort of these middle columns, right? So I can mix and match these different kinds of indexing to do whatever I want. And that was my next example. Cool. So one more common way that I want to talk about for selecting data is oftentimes you want kind of like a vectorized if statement where you've got two arrays of the same shape. And you want to say if some condition is true, then I want the values out of this array. And if it's false, I want the values out of this array. And often where this arises is if you're converting some function that you would naturally write as like a loop with an if statement inside of it, the vectorized version of that tends to be sort of compute just both sides of the if statement into an array and then select the one that you want. So when you want to do that, the function you want to use is np.where. And the way where works is it takes 3 arguments. So it takes a Boolean array of trues or falses, and then it takes an array of like the yes condition, and it takes an array of the no condition. And what it'll do is it'll sort of iterate through all of them at the same time. And whenever it sees a true, it'll take the value out of the yes array. And whenever it sees a false, it'll take a value out of the no array. So an example of where that might be used is we could use this to implement a simple absolute value function. So NumPy has a built-in abs function, but for the purposes of examples, we can imagine wanting to write one ourselves. So here what I'm saying is np.where data greater than 0, right? So the condition is I want values from the first array when the data is greater than 0, and I want values from the second array when the data is less than or equal to 0. And then for the first array, I'm just going to say, okay, when the data is greater than 0, I just want to leave it unchanged. I just want data. And when the data is less than 0, I want to negate it so that it gets flipped. And so what I end up with is I actually end up with a -0 here, so this probably wanted to be greater than or equal to. But what I get is, the absolute values, because of the places where it was negative, we flipped it here. In the places where it was positive, we just kept the original value. So to review selections, we just talked about our basic slicing operations, especially on one-dimensional arrays, sort of are a very natural extension of how Python lists work. When we have multi-dimensional arrays, one of the new features that we gain there is we can essentially apply different selections independently along each axis. So I can slice axis 0 separately from axis 1. And if we have an n-dimensional array, we can do that sort of across all those different axes. Anytime you index with a scalar, you remove a dimension. One place where this often sort of trips people up is if you slice a column out of an array. So actually one thing that I didn't show that I probably should is sometimes you want to slice along a later axis, right? So say I just want this column out of the array. So if I can't just do like data bracket -1, because that means give me the last row when what I wanted was the last column, right? So I need to tell NumPy somehow like skip that first dimension. I want to keep everything there. And the way that you write that is you just put a colon and a comma. So this says sort of like slice everything is the way to read that. If I do data bracket colon comma -1, what I get back is these values here. But one thing you'll notice that often trips people up is that these were rendered kind of as a column in my original 2D array, but because I've sliced these into a 1D array, they're now going to render as a row. So an important thing to remember here is that the like geometric way that NumPy prints this for you, it doesn't necessarily correspond to like how the data structure works. In particular, if you have a 1D array, there's no notion of like a column vector versus a row vector. Once you've sliced a column out of an array, you just have a 1D array, and it's always going to render horizontally for you. So anyway, so indexing with a scalar removes a dimension. When we index with slices, Boolean arrays, or index lists, we always keep the dimension unchanged. You can sort of think of those as filtering operations rather than like slicing or like layer grabbing operations. And then slicing on axis has essentially the same rules as Python lists. Boolean arrays filter to the coordinates where the indexer was true, right? So it says it's sort of evaluating a predicate over the array and saying grabbing all the cases where that came back true. Grabbing an index list sort of iterates through the array and plucks out all the locations where you passed an index. And in particular, that's really useful for sorting and this indirect sorting stuff. And then np.where is sort of like a vectorized if statement that you can use to say I want values from this array if it's true, and I want values from this array if it's false. So with that, we're going to drop in another set of exercises that are going to teach you how to use some of these tools to select values out of an array. 1 or 2 more minutes. So one reason why you might want to explicitly use a random state instead of using random is that it's local to you. Essentially, what all of a sudden if you have random works is there's a global instance of that random state object. Because anything else in the program that does anything random is going to manipulate the state of the random number generator. So for example, if you're doing like multi-threaded things that can cause issues, or like if you're in a test suite and you don't know what order your stuff's going to run, you might want to make sure that you sort of have like local determinism from that. And if you make your own sort of little personal private random number generator, then you know that's going to. So in this case, it probably doesn't matter, but I'm sort of in the habit of just always using random state. But you don't need the negative 1. In the same way that like zeros are implicit there, so you don't put it on the and stuff. Right. Negative 1 is implicit. Actually, negative 1 is just gives you everything exact. All right, everyone. I'm gonna keep going here. I think probably most people aren't totally done with this section, but I want to make sure we get through all the material. So you're sort of again more sort of free to come back to and look at these and revisit these lectures. They'll all be posted online after the fact. But I want to keep going to make sure we cover all the material. So just to recap what we've seen so far again, we've seen creating arrays. We've seen ufuncs, which allow us to vectorize operations across arrays. We've seen selections, which are various ways for us to sort of grab data out of our array and reshape it and reformat to what we want. The next thing I want to talk about are reductions, which are different ways that we can sort of summarize our data along a particular axis. This is important because most of the time when we're doing data analysis, the ultimate goal of what we're doing is to present something to a human being. And human beings are really bad at just reading giant numbers of tables. So in order to present something that's sort of intelligible to a human, we either need to generate some visualization or we need to generate some sort of summary of what our data is. And so often what that means is reducing it, so taking things like the max of the data, the min of the data, the mean of the data, the median of the data. NumPy has built-in tools for doing all these things, and it can do them sort of arbitrarily across the different dimensions of an array. So some examples of some common summaries. I just talked about min and max, sum and product, mean, statistical moments, so like mean, variance, skew, kurtosis. One that's maybe a little more foreign to people that's quite useful is argmin and argmax. So if you take the min or the max out of an array, it's going to give you the value that's the min or the max. What argmin or argmax is going to do is give you the index of the value that's the min or the max. And that's often useful if you want to say like select a row where that's the min of another row or the min of the column or something like that. So just as an example of something, if we pretend that NumPy didn't provide a variance function built in, how might we build one for ourselves? This doesn't match my formula. There we go. So here we're doing the sample variance of our data. So imagine I've got some function that's going to compute a variance on an array X. And what we can see is that there's a bunch of different places where we want to summarize our data, right? So we're going to do X minus X dot mean. And we're starting to see sort of the power of being able to work with arrays and scalars together in this case, because I took my array X, I subtracted after performing a reduction, and now that's sort of a nice quick expression to center my data. Then I can take that whole thing and square that whole thing, and then I can take that whole thing, take the sum of it, and then divide through by its length minus 1. And so just to test that this works, I can go back to the random module, which we saw before, draw 1,000 draws from a normal distribution, and say that, well, the variance of our thing should be about 1, and it is, in fact, about 1. And we can confirm with NumPy's built-in operation that our thing works. So we can do a little bit more interesting things. You know, we saw there if I've got an array of data, I can compute statistical moments on it. But I can do some more interesting things when I have a multidimensional data or multidimensional array. So again, I've just got values from 0 to 30. So if I just do the max on that, I'm always going to get a scalar value. Anytime you do one of these reductions and you don't pass any other information, you're going to get a scalar value. And what it's going to do is basically sort of take the whole array, unravel it into a flat array, and then compute the reduction. So the max of this whole array is just 29. But I can pass this axis argument to the data, and that says, or to max, and what that says is reduce along a particular axis. So if I say reduce along axis equals 0, what that says is sort of iterate column-wise and give me the maximum value from each column. So in this case, it's just going to be the bottom row. I could make this say mean, and then I get the mean over each row. I can make this the min, etc. And then I can switch this to axis equals 1. And what that says is instead of summarizing along the columns, now I want to summarize along the rows. Right, so now what I get back is just a 3-dimensional array, which is the mean along each one of these columns. And again, I could apply this with any of the other reductions that we've seen. Sure.
When you think about these axes things, typically we think about it like, oh, axis 0, row, axis 1, column, right? But then the way Scott put it was axis row is actually column-wise mean, and axis 0 is row-wise. Axis 1 is the mean of the row, axis 0 is the mean of the column. So what's happening is axis equals something is collapsing that particular axis. So that's the way to think about it, right?
Yeah, so another way of saying that is that if I have my shape of my data here is 3 by 10, and I do data.mean axis equals 0, what that's going to say is collapse away the axis that's in the 0th coordinate of that tuple. So I end up with is an array of shape just 10. And if I do axis equals 1, what that says is collapse the dimension where the shape coordinate is at index 1, and that's why I get a length 3 array. So one way to sort of think intuitively about how this axis argument works is it tells you which element out of this tuple is going to go away. That's kind of all there is for reductions. There's not that too much more like fancy sophistication you can get here. So just to summarize reductions, they allow us to perform efficient aggregations over arrays. We can do aggregations over an entire array or along a given axis. And there's all kinds of built-in reductions. So there's mean, variance, median. Count non-zero is an interesting one. So that says count all the values where it's non-zero. You see this come up in things like sparse matrix algebra, where you've got matrices that are mostly 0, but then a couple non-zero elements, and you might care about that. And then min, max, and if we go into things like SciPy or like stats models, say, you get into more sophisticated statistical models where, like, in some sense, most statistical models you can frame as a reduction in some way. So with that, we're going to pop into some reductions exercises. We're going to do this one relatively quickly because I think this one is fairly straightforward. And in this example, we're going to use pandas to read in some real data. So we've got minutely price and volume data for 5 stocks for October of 2017. And the initial cells are going to sort of set you up some arrays to do this. Yeah. So just a point that someone asked me about that I realize isn't as clear as I'd like from the notebook. So in the initial cell, I'm using pandas to read in the prices and the volume CSVs. I'm displaying just the first 5 rows of those data frames with these display calls. And in particular, you see the .head method is what's actually sort of grabbing just the first 5 rows. The arrays themselves are quite a bit larger. So when I'm doing this .values attribute, I'm grabbing a big NumPy array containing all the price values and the volume values, or all the values here. And then timestamps is actually, NumPy has a native datetime representation. So if I do timestamps, for example, you can actually see this is a NumPy array string. That's not what I expected. Huh. That should be, why am I getting, oh, there's also a typo here. The calls to read CSV there should have parse dates equals the string containing DT. Yeah, if you date time exercises, you can also just skip those. But if you're running into trouble there, it's because I forgot to add a call to parse dates here. Yeah. Oops. Make that slightly smaller. Yeah, so before, what I was getting back in that timestamps was an array of strings because I hadn't parsed them into anything. And that means the natural way to do the operations that care about that wouldn't have worked. keep going here, I do want to show one of the solutions to the final problem here, which I think is sort of clever and also just like is surprising to me if you haven't looked at like market data fairly at all. So the question here is compute the average trading volume for each minute of the day aggregated across all 5 stocks. And so what's interesting about this is, at least in this time window, this isn't true in general, unfortunately, but in this time window, all of the days are 390 minutes. And so if you think about each column of the stock price, stock volume data, you can think of it as sort of as a sequence of 22 of length 22 sequences of 390 minutes, where you've got 390 minutes, which is the first day, 390 minutes, which is the second day, 390 minutes, which is the third day. And so one thing that's natural to do on that is if I grab, say, just the volume for Apple, right? So I do volumes, bracket, colon, comma, 0. Then now I can take this and reshape this 1D array into a 390 by 22 array. And now what I've got is an array where each row is a minute of the day, and each column here, sorry, do I have that backwards? I think I have that right. So each row here is going to be a minute of the day, and then each column is a day, right? So one thing you'll notice is that the volume in the first minute is quite a bit higher than the volume in subsequent minutes, and then the volume at the end of the day is also quite a bit higher than in subsequent minutes. And then if I, for example, take this, do I have it right? And say dot mean axis equals 1, and plot it. Sorry, I want plt.plot. And I've gone into insert mode. There we go. You get this nice sort of intraday volume spike chart, which is kind of interesting. Anyway, so I want to move on because we've got about half an hour left, and I want to get through the last 2 sections I want to talk about. So the next section I want to talk about is broadcasting. And the idea behind broadcasting is so far throughout the tutorial, we've talked a lot about how to sort of combine arrays together. And we've talked about operations that work on multiple arrays at the same time. And we've always sort of been working with the implicit assumption that you could only do operations with arrays that were exactly the same shape, because that was the only time where it made sense to kind of line up all the values from each array. And it turns out that that's not quite true, and that there are cases where we can sort of reasonably make sense of what it would mean to align data with different shapes, as long as we have some notion of when shapes are compatible. And NumPy provides a set of rules that we call like the broadcasting rules of the broadcasting system that define or give us sort of a set of rules for how we work with arrays that are compatible in this sense. We've already seen one example of this in a couple cases, right? So we've seen cases where we could combine an array with a scalar value. And what we got there was essentially the same result that we would have gotten if we had combined an array with an array of the same shape that only contained that scalar value, right? So for example, if I do np.I of 3, I'm going to delete this so we got a little more room. I get this sort of triangle matrix here. And if I multiply that by 2, right, then what I get is the same thing that I would have gotten if I had multiplied that whole matrix by an array containing just the value 2. So anytime we do an operation with an array and a scalar, it's sort of as though we had done an operation with an array and an array of the same shape that only contained that scalar. Another thing that is kind of a natural generalization of that is often we have an array whose dimensions are kind of like a subset of an array of the dimensions of an array we already have. A common way to get such an array is when we apply a reduction, right? So if we take an array and say compute the mean along a given axis, we now have an array that matches all the dimensions of our original array except one of the dimensions has been truncated. And what that means is that we could align our means array or our reduced array back with our original array if we could sort of tile it back up and repeat it to make it align with the original array. So for example, say I've got just some random data here. And if I print my data, right, we've just got some values. If I print the mean of my data, I've got a value for each row. And so now, if I do data minus data.mean, what what might we want to happen here? One thing we might want is just that it errors, right? It doesn't know what to do here. But another natural interpretation to give this is to say, take this array of means and essentially repeat it, tile it, stack it on top of itself so that we can then build an array that aligns with our data. And what that means is that we end up doing is that we subtract the mean of each column from that column. And that turns out to be like a really common useful operation in statistics. For example, we often want to like center an array of data so that we can calculate like a covariance matrix or something like that. So this ability to sort of take an array of data, reduce it, and then immediately combine it back with itself turns out to be really useful in a lot of cases. One thing to notice here is that if I do data.mean and I do axis equals 1, for example, so now I've reduced along the columns here. And one thing that we might want to happen here is that if I did data minus data.mean axis equals 1, that would sort of automatically know how to take my array and kind of like turn it sideways and then do that same subtraction row-wise. And it turns out that by itself, NumPy won't do that. So if I do that, I actually get a value error saying that it can't align an array of length 3 with something that's like 3 by 5. And the reason that's the case is that when I have a 1D array, NumPy is going to sort of, when it's trying to tile it in this way, it's going to think about it as though it were a row vector, right? And so if I took that and tried to tile it back up, I'd only be sort of covering, a portion of the array. It doesn't line up naturally the way that I want. And so what I need to do if I want NumPy to broadcast my one-dimensional array in sort of this column-wise fashion that I'd want, what I need to do is actually generate what the closest NumPy has to a column vector, which is a one-dimensional array where one of the dimensions is of length 1. So, for example, what I can do is say data.mean axis equals 1. So that gives me a 1D array. And then what I can do is slice it with colon, comma, np.newAxis. And what newAxis does is says insert into the dimensions of that a sort of synthetic dimension of length of shape 1. So if I actually look at the shape from this, I now have a 3 by 1 array instead of a just length 3 array. And so now we can think of that as sort of an array that's just a column vector. And so what that means is that if I do bracket colon, comma, np.newAxis here, now we get kind of the result that we wanted, where we take this, I'll do colon, comma, np.newAxis. Right, so now we're going to take this sort of what we might think of as a column vector now, and we'll tile it across the array in the way that we want. And then we get this sort of behavior again if we subtract the row mean from each row. This operation is actually so common on reductions that there's a parameter you can pass to mean and to a lot of the other reductions to make this work, which is keep dims. So if I pass keep dims equals true, that does the same thing as doing the reduction and then sort of tiling it down. And the way to think about the name keep dims is saying, rather than reducing from a 2D array into a 1D array, keep me as a 2D array where I'm just sort of one size dimension on that axis. So that's still sort of relatively straightforward, right? We have a sense, I think we kind of have like a spatial intuition for what it means to say, I've got a 2D array, take a row and sort of tile it up, or take a column and tile it across. One thing that I think is a little more surprising to a lot of people is this case. So here I've got a row vector and a column vector, and now I'm going to do row plus column. Who here has a guess on what's going to happen here that hasn't already worked with this or seen this? Who has a thought on what you might want to happen here, or what you might expect to happen here? Somebody's got a guess. Huh? Yeah, so one thing we might expect here, right, is that we get like a matrix that's mostly full of zeros, and we just have like this column is the leftmost column, and this row is the topmost row. I think that's a reasonable thing you might expect. Another thing that you might expect, I think, is what I would have expected the first time, is that this would just be an error, right? I don't have an immediate obvious intuition for how to make sense for this. So I think error is also a reasonable intuition for this. It turns out this is well defined. And what this means is, we talked about what it means to sort of tile an array row-wise, and we talked about what it means to tile an array column-wise. And the observation is that we can align these two arrays if we do that to both of them. So if we tile the row down and we tile the column across, what we're going to end up with is that same 3x4 array. But what ends up happening is we get the result of doing sort of like the pairwise, we take every pair of elements from these two arrays, throw a plus between them, and we end up with an array whose shape is sort of the product of both of them. And again, this works for any kind of binary operator. So I can do row times column, and again, I get this sort of like virtual replacement of the array, or this virtual, ooh, I haven't seen that screen. Right, so any kind of binary operator I can want to do, I can take these two arrays and sort of smear them across each other and get this bigger array whose shape is kind of like the cross product of the two arrays. So that was kind of like a hand-wavy sort of intuitive definition of how this works. There's actually sort of a hard and fast set of rules for what happens here. I'm going to go through them quickly. I don't expect you to like internalize them perfectly just from saying them. But if you go back later and look at the SciPy docs and sort of stare at some examples long enough, I think it'll start to make sense how the rules that I just described fall out of that. So the general sort of rule for how broadcasting works is that if I have two arrays and I want to align them in some sense where it means like I'm going to pass it to a ufunc that needs to do this, then first what's going to happen is that if either array has a smaller dimension, I'm going to make the dimensions the same length by padding ones to the shape of the smaller array. So like in the example where I had a column vector and a row vector, I had a 1D array and a 2D array. And the first thing I was going to do is take the 1D array and make it and add sort of a 1 on it. So if it was a length n array, now it's a 1 by n array. So then now that I have two arrays that have the same dimensionality, the coordinates might not all match, but they have the same number of values in their shape. So then I'm going to sort of iterate pairwise over the shapes. And if the sizes match, great, we already know how to align them. We don't have to do anything. If exactly one of the arrays has a dimension of size 1, then that means that we can make the array match the other one by doing this sort of tiling operation, where we can take this array and kind of extrude it out across that dimension so that we basically repeat it, and now it matches the shape of the array that we had. So if we have exactly one array with a dimension of size 1, then we're going to do that sort of tiling operation. And then if the arrays have otherwise unequal dimensions and it's not the case that one of them is equal to 1, then we raise an error. Then there's nothing we can do. And it turns out from just this set of rules, kind of all the behavior that we just saw falls out. So I know, at least for me, that sort of like rule-based description doesn't really convey a lot of the intuition. So a good way to think about this, I think, is with pictures. So this is a picture taken from scipylectures.org, which is a great resource for all of this stuff. And this is kind of just trying to show visually what happens when we do this broadcasting operation. And so the idea, if I have two arrays that are the same shape, then it's relatively straightforward to see how we combine them. And then what's interesting is if I have a 2D array and this 1D array, then what happens is we take our 2D array and it stays the same, and then we take this 1D array and you can see it's kind of grayed out, but we can sort of virtually tiling it down to repeat it a bunch of times. And what we end up with is the same result. And then when we have the column vector and the row vector, we do the same thing, except we virtually tile one of them along one axis, we tile the other one along the other axis, and then when they combine together, it works. So I mentioned this a little bit previously, but one thing that's often useful for this is if I have two one-dimensional arrays and I want to sort of broadcast them across each other in this way, a thing that's often useful is to convert one of them into a two-dimensional array by using this new axis thing. New axis, by the way, is just an alias of the Python value none. So I could just replace this with none, and it does the exact same thing. The reason new axis is an alias there is that indexing an array with none is not super clear to a reader who doesn't happen to know that has that magic semantics for NumPy. So that's why you'll often see new axis used even though it's the same. So if I take my x, which is a 1D array, I sort of turn it sideways and turn it into a column vector, and then I add them together, what I end up back with is this 2D array where I get the result of sort of doing the pairwise addition between each element of the array. So one thing some of you may have seen in the earlier examples on ufuncs was using np.meshgrid to do two-dimensional plotting. And the way that worked is we sort of built these two-dimensional arrays that together described sort of all the pairs of xy coordinates where we wanted to draw some function. Using this broadcasting stuff makes it a lot easier to do that kind of stuff. So if I say, all right, I want my x's to range from -5 to 5, and then I want my y's to range over the same space but sort of turned sideways, then if I combine these together, I'll have a shape 1 array, a shape 100 by 1 array, and then if I add them together, I get back a shape 100 by 100 array. And then what I can do is if I do like sine of x plus cosine of y, this will get evaluated, and then when I do this plus operation, it's going to sort of automatically do the pairwise addition across all possible pairs. And what we end up with is this nice pretty plot of kind of psychedelic looking cosine function. So to review broadcasting briefly, so NumPy arrays, earlier we had sort of told ourselves that NumPy arrays only could do these vectorized operations when arrays were the same shape. But in fact, we can do these operations on arrays of different dimensions as long as those shapes are still compatible. And the intuition you should have for compatible is that they're compatible as long as sort of I can make them the same shape by taking one of them and like repeating them along some axis of the other array. So one way to sort of give yourself some ways to think about that is that whenever you're doing this kind of operation, and you do a broadcasted operation, the resulting array is always going to be at least as large in each dimension as the largest array is in that dimension. So if I have a 1 by 100 array and a 100 by 1 array, and I combine them in some way, what I'm going to end up with is a 100 by 100 array. And in general, whenever you do this, if it works, what you're going to end up with is sort of the pointwise max along each dimension. So with that, we're going to hop into some of the broadcasting exercises. We've got about 12 minutes left. And I want to make sure I sort of show some of the exercises. So we're going to do, we'll do about 8-10 minutes on these exercises. And then with about 5 minutes left, I'm going to break and just show some of the solutions so you can get sort of a sense of like what a complete sort of fully solved problem with NumPy might look like. Just so people know, if you're using the evaluate linear Bezier curve, there's an error in the 3/4 one. It should be passing 0.75, not 0.25. So if you're using that as to check that your first example is correct, it probably is. So, for the broadcasting exercise also, if you feel like you're stuck or if you want a hint, there is a solutions notebook implemented for this next door. In particular, if you're sort of stuck on the first piece, the solution for the linear Bezier curve more or less generalizes to the quadratic and the cubic Bezier curves, and then the fully general case, you need to do something a little more clever. Sorry, if you're still working on the Bezier curves example, which is probably what I expect because these are pretty hard exercises, especially compared to the other stuff, feel free to keep working on them. I think for these, it's useful to sort of see how a solution for this would actually get constructed. I can walk through a couple of the solutions for this, and also so you can see some of the pretty pictures that come out. So the idea behind a Bezier curve essentially is that it takes this idea of interpolating between 2 points. So the simplest case is of a linear Bezier curve is I've got a point P0, I've got a point P2, and I've got some parameter T that's going to span from 0 to 1. And one intuition you might have for what this formula says is that when T is 0, my function is going to evaluate to P1 or P0. When T is 1, right, this whole term is going to go to 0. This term is going to be 1, so I'm just going to get P1. And when T is some value between 0 and 1, what I'm essentially going to get is the point that's like T percentage of the way between P0 and P1. So it's just going to trace out a line sort of smoothly varying between P0 and P1. And so the way that we can implement this is for the evaluating a single point. So here we've got P0, which is an array, P1, which is an array, and T, which is just a scalar. So we're doing a little bit of broadcasting here, right? So we're going to do T times P1, which is going to give us sort of the percentage of P1 that's going to contribute to our value. We're going to do 1 minus T times P0, which will give us the percentage that P0 is going to contribute to our point. And then if we sum those things together, we're going to get that value that's kind of T percent of the way between the points. And so if we take that, we say that, okay, if we evaluate this at 3/4 of the way through, then we're going to get the point that's sort of 3/4 of the way between P0 and P1. Now, and then the trick is if we want to evaluate that multiple times, if we pass an array of T's, then what we can do is sort of turn T's sideways and evaluate the same expression, but now across an entire array of T's. So for every value from like 0 to 1, sort of evenly spaced here, what we're going to do is compute that exact same expression, but now vectorized across an entire array of T's. So what happens when I turn this sideways is when I do this addition, I end up sort of taking this function and applying it along each possible choice of T in the range that I'm interested in. And what that means is if I take that and then tell matplotlib to draw it, I get this nice picture of a line. So then the case that's a little bit more complex is when we get to a quadratic Bezier curve. So now the idea here is we've again got a sort of a P0, which we can think of as our starting point. We've got a P2, which we can think of as our endpoint. And then what the P1 ends up doing is kind of pulling the curve toward itself. So we're going to get a curve that kind of starts at P0, moves towards P1, and then kind of curves back to P2. And the solution for this ends up looking basically the same. So I'm going to tab over to the other notebook just so I don't type this whole thing out and typo it. So all we're going to do is, again, we're sort of going to compute each of the contributions from each of those points as a separate term. So again, we're going to kind of turn T's sideways so that we can compute all these for each possible choice of T. And then we're going to say, okay, the P0 term is 1 minus T's squared times P0. So it's sort of for each T, 1 minus T squared. And then for the P1 term, we're going to have 2 times 1 minus T's times P1. And then for the P2 term, we're just going to have T squared times P2. So these are all each going to be sort of 2 by len of T arrays. And we're just going to add all those things up to, again, sort of get the point that we're interested in for each T. And so if I take all those things and I draw a point and I ask matplotlib to plot it for me, I get this nice pretty picture of this curve that sort of starts off moving towards P2 and then kind of curves away from it and ends up over here. Cubic Bezier curve has sort of basically the same feel to it. So we've got slightly more complex algebra here, but sort of structurally the shape is still the same. So we've got taking our T's, we're going to vectorize across the T's, and then we're going to say, okay, here's all the like algebra to actually generate those pieces. And then at the end, we're just going to sum all those back together. And so if I take this and evaluate at a bunch of different points, what I get back is this picture of, I get this curve that sort of starts, goes towards this point, and then kind of curves toward this point, and then comes back towards the last point. So finally, what we end up with is this generalized case. And so what's interesting and a little bit trickier about this one is that here for the quadratic and the linear and the cubic cases, we got each of our points separately as sort of individual length to 1D arrays. In the generalized case, now we're actually going to get an array of points. We don't know how many of those points there's going to be to start with. So we're just going to get now sort of an array of points and an array of T's. And the first thing we need to do is, it turns out that the coefficients in these big polynomials actually come out of Pascal's triangle. They're the binomial coefficients. So we can use a ufunc, and it's a special ufunc, which is from scipy.special import comb, which is combinations. So we're essentially going to evaluate n choose k for n equals the order of our curve, and k is one more than that, or might be that minus one. But basically, we're going to grab 4 coordinates. Yeah, so we're going to do n choose 0, n choose 1, n choose 2, n choose 3. So we're going to do n choose k, where k is our order. So this is going to give us all these coefficients. So we're, if we have n equals 3, we're going to get this array of 1, 3, 3, 1. If n equals 4, we're going to get this array of 1, 4, 6, 4, 1. If n equals 5, we're sort of traversing down Pascal's triangle, if you've seen that. And then for the weights, what we want to do is sort of take those binomial coefficients and again do that same tiling operation against all the t's, where now we have sort of 1 minus t squared times the n, or raised to the power of the order of the curve. And when we do this, what we end up back with is essentially for each time t, an array of the weights that we want to use for each point at that time t. And then what we want to do is say, okay, for each time t, we now want to take a linear sum of the points. And it turns out that's actually precisely a matrix multiply. So the last line here is just matrix multiply this array of weights by the points. And so if we ask it to draw that, we get this sort of like interesting looping picture. And if I put more interesting points here, we could get curves that kind of go all over the place and do whatever we want. I don't necessarily expect everyone to have followed every precise detail of that, but I think it's worth, if you're interested in this stuff, to sort of take some time, dig into this example, and get a sense of what the shapes are of the arrays at each point in this evaluation. That's, I think, one of the best ways to think about this is just go down and write down, okay, it's going to be a 50 by 2 array at this point, and then it's going to be like 50 by 2 by 10 array at this point, et cetera. I think that's a good way to sort of build an intuition for what's happening here. And then one more fun thing that we can do with this once we have this point estimator is, so say we've got this function now that says, given an array of points, which are our control points for our Bezier curve, and given a number of samples, we can generate points along that curve. And then what we can do is write an estimator to tell us how long is that curve. And the way that we can do that is if we ask it to evaluate samples, that's what we're doing, samples equals compute Bezier curve. Make this a little bit bigger. Right, so now what we're going to get back from this expression is going to be an array of length n samples by 2, which are all the points along the curve. If I do np.diff along axis 0 there, then what I'm going to get now are points representing sort of the line segments between each of those samples, right? So I'm sort of taking the linear difference between each one of those points. And if you think about what that means, right, it's sort of equivalent to traversing the curve and looking at all the little line segments that connect those points. And as the number of samples gets very small there, the sum of the lengths of all those curves is going to approximate the length of the overall curve. And we can actually sort of compute that, right? So if we have all these delta points, which are these little line segments, we can do square root of deltas squared dot sum, which is going to give us all those lengths. So now we went from a 50 by 2 array to a 50 by 1 array, which is just the lengths of all those line segments. And then finally, if I sum all those things up, what I'm going to get back as a final result here is the length, is an approximation of the length of the curve as a function of the number of samples that I took along the curve. And so if I ask this sort of estimate the curve length, I get some value, and then we can see that if I, for example, ask it to do that at various points, it's going to eventually sort of converge and approach a good approximation. So eventually it's going to converge to about 5.13. One thing that you should be thinking with this last slide is I just spent about 3 hours trying to tell you how to avoid for loops in your NumPy code. And the last slide that I put here is a for loop over the number of samples that I wrote here. And so a challenge for anyone who wants to come back to this notebook later is try to figure out how to vectorize over this estimation process. I would be very interested to see if someone can figure out how to do that. Cool, so we've got about 10 minutes left. So I want to try to give you in these last 10 minutes a little bit of a flavor. Sorry, I'm on the wrong version of this. There we go. A little bit of a flavor of how all this machinery actually works under the hood. I'm going to talk about this for about 5 minutes, and then we're going to wrap up with a little bit of a review, and then I'll let you go for lunch. So we've seen that we've got these n-dimensional arrays, right? And we've been doing sort of various things. We've been reshaping them, we've been transposing them, we've been slicing them. One thing that we haven't talked about that is often a gotcha for a lot of people using NumPy is, so say I've got my data array, and then I do, row equals data 0, right? So row is just a single row. And say now I mutate that row in place. So say I do row 0 equals 100. Who here thinks that that operation will have affected what was in the original data array? All right, we got at least one confident person. I think most of us, at least if you're coming from Python, have the intuition that that wouldn't do anything to the original data array. But it turns out that if I can type, that it does. So this should be pretty surprising to you, I think, if you haven't seen this before. So what this says is when I did data bracket 0, I got an object that sort of came out of data, and when I mutate that object, it somehow is transitively mutating the original data array, right? When I did this write into data, what I actually got, that value is somehow sharing the underlying data with the original data array. And that should be probably a little bit surprising to you. And so it turns out that what happens when I do this slice operation is under the hood, a numpy array is essentially 3 things, or 4 things here, say. So ignore this sort of giant scary byte string for a second and just concentrate on the first 3 things. So I've got my data array here, right? And semantically, this prints to us as this 3x4 array. We talked a little bit earlier about the D type, right? So the D type sort of tells us what kind of values can be stored in the cells of this array. And we've seen shape a bunch of times before here, which is telling us this is a 3x4 array. One thing that we haven't talked about so far is strides. And then finally, what we really haven't talked about is this data, which you'll see I got from doing data.data.2 bytes. And so it turns out what's happening here is that under the hood, the way that a numpy array is actually represented is it's essentially just a big array of bytes plus some additional metadata about how to interpret those bytes. So in particular, right, it knows that that array of bytes should logically represent an array of a certain shape, where each element of the array is of a particular size, right? So an int64 means that sort of every 8 bytes of that sort of just buffer of data should be interpreted as a 64-bit integer, and the next 8 bytes should be interpreted as a 64-bit integer, et cetera, et cetera, et cetera. And then we've got the shape here. And so one thing that you might be asking is, well, we've talked a lot about multidimensional arrays, but ultimately memory in your computer is flat, right? So NumPy has to have some sort of way to translate from n-dimensional coordinates into a physical location in memory where a given integer value is actually stored. And the thing that tells it that is this strides information. So the way to read this is if I have a 2-dimensional array and I want to find the integer value or the value in the array at coordinates x, y, then what stride says is I have to go x times the first stride bytes from the start of the buffer, and I have to go y times the second stride bytes from the start of the array to get there. So for example, if I want to find the integer value in this array at coordinate, say 1, 2, what that says is I have to go 32 bytes to get to row 1, and I have to go 8 bytes to get to traverse a column. So if I want to go to 1, 2, I have to go 32 bytes plus another 8 bytes plus another 8 bytes because I need to go 2 columns there. So an easy way to read this as often is that the strides tell you to move sort of 1 unit in each direction. How far do I need to go in memory, right? So what this stride tells me is that if I want to go from one column to the next column, I need to go 8 bytes. But then if I want to go from a row to another row, well, I have to skip over 4 values to get there. So it's going to be 8 bytes times the length of a row, which is how I got 32 here, right? So what this is saying is that in order for me to get from here to here, I have to skip this whole row in order to get there. So that's sort of interesting. So how does that relate back to the kind of mutation thing that I talked about earlier? One of the things that this buys us is that it means that we can make arrays that sort of look and feel like copies of an array, and we can do it really, really cheaply, right? So say I take data and I do data bracket 1 colon here, right? So now I've chopped off the first row of the array, and you might sort of naively expect, and I think most people sort of expect when they first come to NumPy, that what this would have done was just copy all of the data into a new array. And it turns out that's not what it does, because we don't need to do that in order to, actually I'm going to do, data bracket colon 1, print r, and I'm going to copy here so I can put different expressions so you can see what I do. Right, so if I have an array that's 3 by 4 and I want to chop off the first row, I don't actually need to copy any of the underlying data. All I need to do is sort of slide forward the start of the buffer and change the shape that tells the array sort of what coordinates are legal. But otherwise, I can just reuse the same memory. And in particular, I can keep using the same strides information, because as long as I say, okay, from the base of wherever data is stored in my array, if I need to move down a row, I need to move 32 bytes. If I need to move along a column, I need to move 8 bytes. That sort of will continue to have all the same values that we might want. And so one thing you can do with this is you can do very cheap, efficient slicing. The downside of this is that because we're actually sharing memory, if we mutate that slice, that mutation is actually happening on the same underlying data. And so you need to be careful with this when you're mutating arrays. One of the things that's kind of neat about this is that this can actually express quite a lot more of the operations than you might think. So for example, one thing that I think many people have the intuition for is that this operation, the : 2, that get every other element, I think most people would expect that this is a copying operation, and it is not. So if I do this, right, so if we think about what needs to happen in order for me to copy every other element out of this buffer, right, so I'm just going to go back to saying r equals data for a second here. Right, so if I want every other element out of this buffer, then what that says is I want this row and this row. And if I had more rows, right, it would keep going. And what we need in order to be able to represent an array is a pointer to a start of data, which we can have, because we're going to have the same start of the data. And then we need a set of rules for how to go from a given index to another given index. And in this case, all we need to be able to say is whenever you would go from this row to the next row, you need to skip one of the rows that was in the previous data. And we can do that by just telling NumPy that the strides is twice as long as it would have been. So if I do data bracket : 2, right, I'm actually still using the same data, but all that happened was that we doubled the stride there. So I think that's sort of neat. And you can actually you can play really interesting tricks with this. So for example, a case that I like to show people to sort of bend their brains around this a little bit is if I do data equals np.arange 5, and then there's this function called np.lib.stridetricks.as, right? Am I out of time or? Wrapping up, okay, cool. I'm not gonna show this, I'm gonna do the review. If you wanna see some sort of unusual abuses of this system, come find me afterwards and I'll talk to you about it. So wrapping up and sort of coming back to more reasonable uses of NumPy. The stuff that I was going to talk about is sort of useful for building intuition. You probably shouldn't build software with it, which is a good description of a lot of the things that I work on. Cool. So wrapping up all the things we've talked about today. So if you take nothing away from the lecture today, what I want you to take away is this. So numerical algorithms are slow in pure Python because the overhead of interpretation and dynamic dispatch operates our runtime, or dominates our runtime. Whenever we want to do the same thing over and over and over and over in a loop, any sort of little extra costs we add at every iteration of that loop is going to end up dominating our performance. And so the fact that we have to do dynamic dispatch on methods and on binary operators, and even just on the interpreter loop itself, interpreting instructions, over time for very large arrays, that ends up sort of killing our performance. And so NumPy solved this problem in two important ways. So one of them is it imposes additional restrictions on the contents of arrays, and that allows it to switch from dispatching on every element of an array to just dispatching once per array or once per logical operation. So it means that our problem is now is no longer getting slower proportionally to the size of the array. It's only getting sort of slower, at least for the overheads that Python imposes, slower proportionally to the number of operations we're going to do. And that's typically much, much, much smaller than the sizes of our arrays. And then in particular, the way that it can take advantage of those restrictions is that it can take the inner loops of our algorithms, instead of running them in pure Python that's doing all this dispatching, it can run them in compiled C or Fortran code. And finally, using NumPy well really requires reworking algorithms to use vectorized operations instead of for loops. So if you just take your Python code and translate it and just use NumPy arrays but don't change anything about it, you're not going to see better performance. In fact, you're likely going to see worse performance. So in order to sort of use NumPy well, you have to kind of rethink about how you solve problems. But I often find that the resulting solutions that use idiomatic NumPy come out sort of simpler and faster, certainly faster, and often sort of simpler and clearer. I find that the restrictions often kind of have a clarifying effect on my understanding of a problem. Finally, to wrap up the specific things we talked about ufuncs, selections, and reductions as kind of your core toolbox for building algorithms with NumPy. And then we talked about broadcasting as the system that allows you to naturally generalize those algorithms over multiple dimensions and kind of acting as the glue that makes all those other things work together nicely. And finally, we saw that strided memory is this sort of efficient, flexible underlying representation for arrays that allows us to do things like very cheap slicing or very cheap viewing of other arrays, but it can cause confusion, it can cause subtle bugs when we mutate arrays because it's not always clear whether changing one array will affect some other array. Finally, I want to close. So I'm Scott Sanderson. You can find me on the internet on these places. There's a survey link for the tutorial up here. So if you want to tell people whether or not you like the tutorial, you can put that up there. You can find the materials from this tutorial on my GitHub. So it's github.com/ssanderson/foundations of numerical computing. If you want to keep your versions of the exercises, like the notebooks that you've been working on and you've been working on the remote server, I recommend you download them now because I will take down that server sometime this afternoon. But you can get fresh copies of the notebooks on the GitHub, and sometime in the next 2 days, I'm also planning on posting solutions to the different exercises we saw today. And I think with that, we are all out of time, and I will let you go for lunch. So thank you all for your time.